Hello everyone, this chapter will talk about technical principles of Hive. We all know that the size of datasets being used for every industry is growing rapidly. Hadoop was the solution for large data storage, but using Hadoop was not easy for end users. Hive is an easy way to work with data stored in HDFS. Basically, you can just think Hive as SQL for Hadoop clusters.
So after this course, we'll be able to know Hive application scenarios and basic principles, enhanced features of Fusion inside Hive, and some common Hive SQL statements. First, let's take a look at the introduction to Hive.
So Hive is an open source data warehouse system on top of HDFS that adds structure to the data. It can support PB-level distributed data query and management. It also provides the following functions: flexible ETL, supporting computing engines such as MapReduce, TAS. TAS here is an application framework which allows for a complex DAG of tasks for processing data, and Spark, direct access to HDFS files and HBase, and is easy to use and program. Here, one more thing to notice. Some of you may be confused about data warehouse and database. Data warehouse is a system used for reporting and data analysis. Generally refers to the combination of many different databases across an entire enterprise. It usually stores historical data so that all of the relevant data may be used for analysis. Database is an organized collection of data. Data from various sources are collected into a single place. This place is the database. It usually stores current data for querying. The main difference between them is that database is used for online transactional processing, while data warehouse is designed for online analytical processing to analyze questions that are critical for your business. Consider the scenario where a bank ATM has disbursed cash to a customer but was unable to record this event in the bank records. If this started happening frequently, the bank wouldn't stay in business for too long. So the banking system is designed to make sure that every transaction gets recorded within the time you stand in front of the ATM machine. These records form a database, but suddenly your manager asks for a report about maybe customer group for financial products. You cannot analyze the problem based on the database because it changes due to various updates. That's why we need a data warehouse where we can extract historical data from different sources and make analysis for specific problem. Hive is built on Hadoop for static batch processing. Hadoop has long latency and consumes a large number of resources during job submission and scheduling. Hive does not support quick query of data in a large-scale dataset. For example, querying data in hundreds of MBase dataset has minutes of delay. Therefore, Hive is inapplicable for scenarios where require low latency. For example, online transaction processing. So in actual application, Hive can be used for data mining, non-real-time analysis, data aggregation, and data warehouse. More specifically, Hive can be used for user behavior analysis or interest analysis. Hive does not support real-time query. We can use Hive for network log analysis, text analysis, and also some report analysis. In Fusion inside Hadoop, at the bottom is HDFS and HBase, which are used to store the datasets. Then is Yarn that manages and schedules resources for applications. MapReduce, Spark, tasks are distributed parallel computing engines. On the top is Hive, a platform used to develop HQL like SQL scripts to do MapReduce operations by default. All Hive data is stored in HDFS. And here is the comparison between Hive and traditional data warehouses. They are compared from the following aspects. For storage, we know that Hive is based on HDFS, so it's infinitely scalable, but traditional data warehouses are of limited storage capacity. Hive can take MapReduce or TAS or Spark as the execution engine, while traditional data warehouses use algorithms with higher efficiency to query data. They are also compared from usage, flexibility, analysis speed, index, usability, and so on. Hive has some advantages. For example, Hive Server, which is a process for Hive to provide external SQL services in cluster mode, Dual Metastore, which provides metadata information, and a query retry after timeout, make sure high reliability and tolerance of Hive. It uses SQLite query. We can define functions and storage formats, and Hive also have multiple interfaces like Beeline, JDBC, Thrift, Python, and ODBC. But Hive also has some disadvantages. To be more specific, Hive uses MapReduce as execution engine by default, so it has high latency. And Hive doesn't support materialized fields. Data updating, insertion, and deletion cannot be performed on fields. Besides, Hive is inapplicable to OLTP, which is online transactional processing. We cannot add, update, and delete column level data. And last one is that Hive does not support storage process, but supports logical processing using user-defined functions. Storage procedure is similar to UDF. To save time and memory, extensive or complex processing that requires execution of several SQL statements can be saved into storage procedure, and all applications call the procedure. The major difference between storage procedure and UDF is that UDF can be used like any other expression within SQL statements, whereas storage procedure must be invoked using call statement. Okay, next, let's take a look at the structure of Hive. Let's look at the core part of Hive, driver. It manages the life cycle of HQL execution and participates in the entire Hive task. Driver is composed of three parts to break down the Hive query statements: compiler, optimizer, and executor. By default, compiler is used for compiling HQL statements into graph of map and reduce tasks. These tasks are interdependent. As for optimizer, there are logical optimizers and physical optimizers to optimize HQL execution plans and MapReduce tasks respectively. And executor is used for executing map and reduce tasks based on task dependencies. So driver is the most important part of Hive, the core of Hive. Also, we have Metastore, which stores metadata of tables, columns, and partitions. Driver can connect with Metastore to get any information about data if it needs. While Hive is a data warehouse infrastructure software that can create interaction between user and HDFS. The user interfaces that Hive supports are Hive Command Line, Hive Web UI, JDBC, and ODBC. Users can use command line interface to directly connect with Hive. And Web UI is a visual structure on Hive used for interaction with data, but users cannot directly use JDBC or ODBC to interact with driver. We need a Thrift server, which provides Thrift interfaces as the servers of JDBC and ODBC, and integrates Hive and other applications. In Fusion inside Hadoop, Hive contains the following components: Hive Server, Metastore, and Web HCAT. Hive Server provides Hive database services externally, translates SQL statements submitted by users into related YARN tasks or HDFS operations to complete data extraction, conversion, and analysis. And multiple Hive servers can be deployed in a cluster in load sharing mode. Metastore provides Hive metadata services as well as reads, writes, maintains, and modifies the structure and attributes of Hive tables. Metastore also provides Thrift interfaces for Hive Server, Spark, WebHCat, and other Metastore clients to access and operate metadata. Multiple Metastores can be deployed in a cluster in load sharing mode. WebHCat provides REST interfaces and uses them to run the Hive command to submit MapReduce tasks. Multiple WebHCats can be deployed in a cluster in load sharing mode. As shown in the figure below, developers make HTTP requests to access Hadoop MapReduce, Pig, Hive, HCatalog DDL from within applications. Data and code used by this API are maintained in HDFS. HCatalog DDL commands are executed directly when requested. MapReduce, Pig, and Hive jobs are placed in a queue by WebHCat servers and can be monitored for process or stopped as required. Developers specify a location in HDFS into which Pig, Hive, and MapReduce results should be placed. Note that the current version does not support Pig interface. In the order of granularity, Hive data is organized into database, table, bucket, and partition. Database is used to avoid naming conflicts for tables, fields, partitions, columns, and so on, and can also be used to enforce security for a user or group of users. If the database is not specified when a table is created, the default database is used. And tables are homogeneous units of data which have the same schema. A table corresponds to a directory in HDFS physically. Hive organizes tables into partitions, a way of dividing a table into coarse-grained parts based on the value of a partition column, such as a date. Using partitions can make it faster to do queries on slices of the data. To take an example where partitions are commonly used, imagine log files where each record includes a timestamp. If we partitioned by date, then records for the same date would be stored in the same partition. The advantage to this schema is that queries that are restricted to a particular date or a set of dates can be answered much more efficiently because they only need to scan the files in the partitions that the query pertains to. Notice that partitioning doesn't preclude more wide-ranging queries. It is still feasible to query the entire dataset across many partitions. A table may be partitioned in multiple dimensions. For example, in addition to partitioning logs by date, we might also sub-partition each date partition by country to permit efficient queries by location. A partition corresponds to a subdirectory of the directory where a table resides, and tables or partitions may be subdivided further into buckets based on the value of a hash function of some column of the table to give extra structure to the data that may be used for more efficient queries. For example, bucketing by user ID means we can quickly evaluate a user-based query by running it on a randomized sample of the total set of users. A bucket corresponds to a file under the path where a table or partition resides. There are two reasons why you might want to organize your tables or partitions into buckets. The first is to enable more efficient queries. Bucketing imposes extra structure on the table, which Hive can take advantage of when performing certain queries. In particular, a join of two tables that are bucketed on the same columns, which include the join columns, can be efficiently implemented as a map-side join. The second reason to bucket a table is to make sampling more efficient. When working with large datasets, it's very convenient to try out queries on a fraction of your dataset while you are in the process of developing or refining them. We'll see how to do efficient sampling at this end of the section. Note that it's not necessary for tables to be partitioned or bucketed, but these abstractions allow the system to prune large quantities of data during query processing, resulting in faster query execution. There are two types of tables in Hive: managed table and external table. When you create a table in Hive, by default, Hive will manage the data, which means that Hive moves the data into its warehouse directory. Alternatively, you may create an external table, which tells Hive to refer to the data that is at an existing location outside the warehouse directory. The difference between the two table types is seen in the create or load and drop semantics. Let's consider a managed table first. When you create or load data into a managed table, it's moved into Hive's warehouse directory. If the table is later dropped, the table including its metadata and its data is deleted. It bears repeating that since the initial load performed a move operation and the drop performed a delete operation, the data no longer exists anymore. This is what it means for Hive to manage the data. An external table behaves differently. You control the creation and deletion of the data. The location of the external data is specified at the table creation time. With the external keyword, Hive knows that it's not managing the data, so it doesn't move it to its warehouse directory. Indeed, it doesn't even check whether the external location exists at the time it's defined. It's a useful feature because it means you can create the data lazily after creating the table. When you drop an external table, Hive will leave the data untouched and only delete the metadata. But how to choose which type of table to use? In most cases, there is not much difference between these two, so it's just a matter of preference. Well, in general, if you are doing all your processing with Hive, then use managed tables. But if you wish to use Hive and other tools on the same dataset, then use external tables. A common pattern is to use an external table to access an initial dataset stored in HDFS. Then use a Hive transform to move the data into a managed Hive table. This works the other way around too. An external table can be used to export data from Hive for other applications to use. Hive provides multiple built-in functions, such as mathematical function, date function, and string function. If built-in functions are not enough for users, Hive also supports self-defined functions. Based on Hive provided by the Hive open source community, Hive Infusion Inside HD has a lot of features that customized for enterprises, such as co-location table creation, colon encryption, and syntax enhancement. HDFS colocation is the data location control function provided by the Hadoop distributed file system. The HDFS colocation interface is used to store associated data or data on which associated operations are performed on the same storage node. Hive supports the HDFS colocation function when Hive tables are created. After the locator information is set for table files, data files or related tables are stored on the same storage node to ensure convenient and efficient data computing among associated tables. And this is a command for how to implement Hive colocation. First, use HDFS interface to create group ID and locator ID, for example, and then create tables with specific group ID and locator ID. Here notice that you must use the insert statement to import data to this type of table to make the HDFS colocation feature take effect. And file format can only be text file and RC file, which is record columnar file. Hive also supports encryption of one or multiple columns in a table. When creating a Hive table, you can specify the columns to be encrypted and encryption algorithm. When data is inserted into the table using the insert statement, the related columns are encrypted. Hive column encryption does not support the field and Hive over HBase scenarios. Hive supports two column encryption algorithms currently, AES and SMS4. Here shows an example of encrypting the phone column and the address column using the AES algorithm. Due to limitations of underlying storage systems, Hive does not support deleting a single piece of table data. But Fusion Inside HD Hive supports deleting a single piece of HBase table data. Using specific statements like this, Hive can delete one or multiple pieces of data from an HBase table that matches the expression. And with the controlling traffic feature, users can control the following things by configuring these parameters in Fusion Inside Manager. Why add this feature? Because there are too many requests of clients, it may cause the restart of the client. So Fusion Inside Hive supports to control the connection of users. In most cases, a carriage return character is used as the row delimiter in Hive tables stored in text files. That is, the carriage return character is used as the terminator of a row using query. However, some data files are delimited by special characters other than a carriage return character. Fusion Inside Hive allows you to use different characters or character combinations to delimit rows of Hive text data. Look at these steps. User needs to set the input format and output format first when creating a table, and then specify the delimiter in this way. So with all these features, Fusion Inside Hive is better than the community version in reliability, tolerance, scalability, and performance. Then let's take a look at some basic operations of Hive. While HQL is the query language of Hive, which is very similar to SQL, and also includes three types: data definition language, data manipulation language, and data query language. Here makes a few examples of Hive basic operations. First is to create a managed table. If not exists is used to create a table if the table doesn't exist. Example employee is the table name, and then give the field name, type, and a comment, which is optional. This line specifies the row delimiter as comma and stored as a text file. And the difference of creating an external table is to add external here and also specify the storage location. This statement is to modify the column after the date in company column into money with string type and this comment. To add columns to an existing table, given the table name, the column name, and its type. This statement is to change the file format into text file, and you can delete some records of a table given the condition. After using the job statement, the table doesn't exist anymore. This statement is to list columns and column types of a table, and this one will show the statement of how to create this table. And here are some commands for how to load data, import or export data. Notice that when data is imported to a Hive table, a data validity check is not performed. It's only performed when data is read. Where is used to give query conditions, and group by means to divide a dataset into several small datasets based on certain rules. And data process is performed on the small datasets. Data can be grouped by using the aggregation function. Union all is used to combine result sets of two or more select statements. The result set can contain the same value. We can join two tables with the same column, and when a query item is the condition of another query item, this is called subquery.
So this chapter mainly talks about Hive, like its basic principles, application scenarios, enhanced features in Fusion Insight, and also some common Hive SQL statements.
Okay, that's all for Hive. Thank you.